Yeah, hello everyone. We hope everyone is in good spirits. In this presentation, we will be describing Perigee, an efficient peer-to-peer network design for blockchains. And this work is the result of a joint collaboration between researchers from University of Washington at Seattle and the Ohio State University. We hope you will enjoy our presentation. Blockchain is a state machine replication for maintaining a public ledger of transaction across various nodes in a peer-to-peer network, which guarantees Byzantine fault tolerance. Blockchain uses a computational power-based consensus protocol to achieve a consistent view of state machines across different peers. Well, there has been many SMR-based systems for maintaining ledger. So what is different about blockchains? The key difference in blockchain is that there is no permissioning authority which decides which are the end nodes that can participate in the network. And the permission is mediated by resource. For example, in proof of work, the amount of power or hashing power that you have controls your participation in the network, thus preventing Sybil attack. The technology of blockchain was first used as an underlying technology in Bitcoin, a cryptocurrency that was launched by Satoshi Nakamoto in 2008. Since then, there has been other cryptocurrencies using blockchain, and today the total market capitalization of cryptocurrencies stand at more than $300 billion. In recent years, blockchain is being used for other distributed applications to remove any digital intermediaries. These digital intermediaries could be software sitting between the user and the customer. Examples being gaming, exchange market, social network, etc. Established companies like IBM, Facebook, Visa, Nestle, and others are also launching their own blockchain systems. This enthusiasm for blockchain stems from its application and potential to be disruptive in so many areas of economic activity.
A key problem facing blockchain systems today is scalability. Bitcoin is a popular blockchain system, so we take it as an example. The Bitcoin network can currently support a maximum of only 10 transactions per second, compared to 1,700 transactions per second on Visa. The transaction fees for Bitcoin may be as high as $30, while there are only few cents at Visa transactions. Bitcoin users maintain a 260 gigabytes blockchain, and all the payments need around 1 hour to be confirmed, while Visa consumes little storage at user side and has few seconds confirmation latency as a centralized system. If the confirmation latency is 1 hour, it's really not possible to use Bitcoin as well as most blockchain systems at payments. In this talk, we will mainly focus on the confirmation latency. There are 4 layers of blockchain that correspond to the normal operation of blockchain system. Many proposals have been put forward to improve the scalability in Bitcoin in each of these layers. At the bottom, there is the P2P layer, whose function is to broadcast messages such as blocks or transactions to all the nodes in the network. There have been proposals to compress or code blocks to speed up this broadcast. Above that, we have the consensus layer for ensuring agreement of state across the users. Proposals such as Algorand and Prince suggest native consensus protocols with more efficient throughput and latency guarantees. Next, the sharding layer allows each node to store only a small piece of the blockchain to reduce storage. Finally, at the application layer, there are off-chain scaling solutions such as the Lightning Network that are built on top of the blockchain. These applications use the blockchain only for mediating disputes in transactions. Since the P2P broadcast is fundamental to all these layers, making the P2P network efficient would benefit all the proposals. So the question we focus on is, can we structure the topology of the network so that the message propagation delay in the P2P network is minimized? Since Bitcoin is a popular example of a blockchain system, for the rest of the talk, we will focus on how to make Bitcoin's P2P efficient. Bitcoin today follows an unstructured random P2P overlay, where nodes broadcast their messages to the random selected neighbors. The consensus algorithm is the longest chain protocol that accepts the longest chain of the blocks wherever there are conflicting forks in the blockchain. And the application is payments between nodes.
Bitcoin today follows a random topology. Under the random topology, a node chooses 8 peers uniformly at random from across the world as its neighbor. However, using random topology to form the peer-to-peer network is inefficient. To illustrate this inefficiency, suppose a node in New York City mines a block and broadcasts it to everyone. If you look at the shortest path that the block would take to reach Tokyo, it might look something like this. The route takes the block all across the world before reaching its final destination. To formally analyze this inefficiency in random topology, we use a result from network systems literature. The result says that if you measure the point-to-point round-trip time between different computers in the internet, then you can embed these points into a d-dimensional metric space such that the metric distance between any pair of nodes closely match their measured point-to-point round-trip time between them. Therefore, we can use this embedded space to study the inefficiency of the random topology. Towards that end, we take a d-dimensional metric space in which endpoints are chosen uniformly at random to become peers in the peer-to-peer network. Under random topology, each peer in the peer-to-peer network chooses log n of these peers uniformly at random as its neighbors. Now the shortest path between any 2 points, say x and y here, in the embedded metric space would look something like this. Observe that the shortest path is much longer than the geodesic shortest path between x and y. The gap between the shortest path and the geodesic distance is encapsulated by this result from computer science theory that says that shortest path between any 2 points under random topology can be logarithmically worse than their geodesic distance. Naturally, our next question is, can we have a different peer-to-peer topology that reduces the gap between the shortest path between any 2 points in the metric space and their geodesic distance? The answer is yes. There is a topology called random geometric graph that achieves the optimal. The topology is constructed as follows. Each node first considers the node within a ball of certain radius r around it. Among those nodes, it connects to a random subset of them. Previously, we have seen that random topology gives shortest path between any 2 points that is logarithmic worse than their geodesic metric distance. Compared to that, in the random geometric graph topology, the shortest distance between any 2 points is just constant factor away from the geodesic metric distance between those 2 points. Here in the right picture, we'll illustrate this improvement by tracing out the shortest path between the same 2 points. However, random geometric graph falls short of addressing heterogeneities present in the internet. For instance, users could have a different bandwidth, which leads to different transmission delays across the network. Also, users could have different processing power, which leads to different node processing delays. The non-uniformity in mining power leads to non-uniform generation of blocks across the network. Additionally, IP addresses may not represent the actual geographic distance due to pervasive use of Tor. This makes finding the optimal topology a non-trivial problem. There has been many works in the past to address the problem of latency in broadcast in peer-to-peer network. These works are broadly divided into structured and unstructured topology. Some of these works try to take neighborhood into consideration, but none of them addresses all the heterogeneities that we discussed in the previous slide. In our work, we present a decentralized algorithm called Perigee that takes into account all these heterogeneities while giving an efficient solution. In Perigee, a node selects its neighbor by exploiting the information from its past interactions with them. The node retains those neighbors that relay the newly broadcast blocks fast, while disconnecting from those neighbors that do not relay the blocks fast. At the same time, it explores unseen neighbors. This exploration flavor is motivated by the multi-arm bandit problem. Casting this topology finding problem into an instance of the multi-arm bandit problem is one of our key contributions. Perigee also automatically adapts to network heterogeneities like hash power, link latency, bandwidth, etc., all of which can vary with location and time. We empirically show that Perigee achieves 33% faster broadcast than random topology. Going back to our toy example for no node delay, Perigee gives us a shortest distance between any 2 points that is very close to their metric distance. Moreover, a node following Perigee protocol might include faraway peers as its neighbors, which leads to very few hops, thus giving advantage over random geometric graph. On the other hand, as you increase the node delay, the shortest distance between any 2 points increasingly starts to look like random topology. The reason behind this is that if your node delay is large, what really matters is the number of hops. However, in this extreme 2, Perigee gives fewer number of hops as compared to random topology. Before we present the protocol in detail, we present the network model and formalize the problem. We consider a round by round model where in each round one block is mined and broadcast to the network. Each node V has a fixed hash power, h of V, that denotes the probability with which that particular node mines a block in a round. And once a block is mined, the node is going to broadcast the block through the network. Now, when a block is broadcast by the node, it encounters two types of delay. One is node delay and the other is link delay. Between any two nodes in the network, we assume there is a link latency L of UV. And for each node U in the network, we assume a node processing delay called D of U that involves, for example, block verification. When a node receives a block, it immediately starts sending the block to all of its neighbors through flooding. Also, for each node, we assume it has a fixed degree bound. That is, it can connect with at most fixed number of neighbors at a time. A node can form a connection to any other node it wants to under this degree bound. Our goal now is to find the best topology such that the 90 percentile delay for broadcast is minimized. By 90 percentile delay, we refer to the time it requires for a broadcast message to reach 90% of the nodes in the network.
Here's a simplified example when a node connects 4 neighbors. The score reflects how fast this subset of neighbors are relaying blocks to the node. We will explain more on how the score is computed in the next slides. For example, this group of 1, 2, and 3 can be assigned a score of 60 milliseconds. The second group can have a different score, so on and so forth. In the second step of the algorithm, node M will retain the subset that has the best score, and it disconnects from the remaining neighbors. In our example, the subset of 1, 2, and 3 has the best score with a latency at 60 milliseconds. These connections will be retained by M. And instead, node M is going to randomly select a neighbor from the list of the other nodes in the network, and it's going to form that as a false connection. The first step as choosing the neighbors with the best score is the exploring part. And the second is the exploration part. We make the neighbor switch decision by every k rounds. Each round, nodes record their neighbor's delay performance by their block forwarding delays. For example, at round 1, the miner mines the block B1 and broadcasts it to the network. M has 4 neighbors. They all receive B1 somehow and forward it to M. M records the block message arriving time from each neighbor, leaving the earliest time between 1, 2, and 3 as a performance as the first subset, then the same as the next 3 subsets. For the next block B2, M records the neighbor's message arriving time again and stores the subset performance, so on and so forth. After k rounds, we get a subset score table of all the subsets. However, The other nodes except the miner cannot know when the block B1 is mined. Also, all the nodes' local time are not synchronized at all. Each round, OR node M can access the local timestamp for the block message time arriving, but cannot know when the block is mined and how long it takes to broadcast from the miner to the M through M's neighbors. Here, we compute the mean of each row, which is the earliest time for M to receive from the miner. Take the first subset as an example. We use the relative time between the time we first hear from the block and the time we first hear from the subset. The score for each subset is computed as a 90% value at each column. We also consider other fast scoring method that maintains the score for each individual neighbor, except for measuring the empirical 90 percentile. We also consider the confidence bounds by the time we receive from the neighbor. More valid block messages lead to a narrower bound, which means more confidence on the empirical 90 percentile. We simulate a network of 1,000 actual Bitcoin nodes obtained from the real dataset, and the latencies are also from the actual measured latencies. Here are some baseline algorithms that will be compared in the later results. We first consider the random topology, which has been discussed before. We also consider a Calamila structure over relay. There's huge of work in peer-to-peer community in designing structure over relays. Calamila is a popular one. The geographical algorithm is to build the neighbor connections by the geographical information. For example, we cluster all the nodes into 5 clusters. Each node makes the most connections in their same cluster, and keeps at least one connection in each other cluster, which may be far away. To find the lower bound of the delay, we also simulate on a complete graph where all the nodes are directly connected. We evaluate the performance of Perigee and compare it against the baseline algorithms. For each node, we record their delay to all the network and select the delay to 90% of the network nodes. Then we sort this 90% delay in the result figure. The x-axis is the node index, and the y-axis is their delay to 90% of the network. The red line represents the 90% delay distribution of the random algorithm. The black line represents the 90% delay in the all-connected network, which is the lower bound. The blue line is the delay distribution of our Perigee subset algorithm, which achieves around 33% compared to the random neighbor selection. The yellow and the purple lines are delay distribution by the geographical and the Calamila algorithm.
Many alternate solutions have been proposed for reducing latency in broadcast. For example, Bloxroute, Fiverr, Falcon, etc. The underlying structure of all these solutions are the same. There is a carefully planned network of fast relay servers placed in selective locations around the world. Whenever a block is mined in a node, it is broadcast to the nearby nodes via the traditional peer-to-peer network. On the other hand, for broadcasting it to far-off nodes, say in another country or continent, the block is first sent to one of the nearby servers of the fast relay network. Then using the relays, the block is relayed to peers in other corners of the world. The two main disadvantages of such a fast relay network is that one, designing fast relay network requires a lot of handcrafting with careful selection of server locations with excellent internet connectivity. This can potentially make fast relay network vulnerable to the heterogeneous behavior of the peer-to-peer network. Second, such a fast relay network where the servers are being managed by a few entities can make the whole system susceptible to the fallacies of centralization, which defeats the purpose of decentralized peer-to-peer network in the first place.
We simulate a fast relay network by selecting 10% of the nodes as fast relay nodes. These 10% nodes occupy the most hash power in the network and enjoy much lower propagation delay. Then we apply the same algorithm and record their delays to the 90% of the whole network's hash power. The results show that Perigee can exploit and explore the network to get much closer to the ideal delay in a fully connected network compared to the baselines. We have proposed Perigee, an adaptive algorithm motivated by the multi-armed bandit problem that finds efficient P2P topologies for reducing block propagation times in blockchain networks. While we have empirically illustrated the effectiveness of Perigee, we believe our work is only a first step and important questions. Theoretically, analysis of Perigee, like to study its convergence behavior, is a crucial topic for future research. In Perigee, one way to launch an Eclipse stack is for an adversary to provide blocks earlier than other nodes, thus gaining a peer's trust and dominating its neighborhood. A formal analysis of this is left for future work. Another dimension of analysis involves analyzing the performance on the node churn, with limited peer addresses known at each node.